Good morning everyone, thank you for joining me. I'm Mr. Ish. We are presenting a part 2 video here on natural logs. I have talked quite a bit about natural logs, not just in this video and the one previous to this one, but in a video or two before. The only reason why I'm stressing or talking so much about natural logs is because as a functional type, they're very important in terms of applicability or in terms of the abundance of questions that you see with regards to integrals and derivatives for natural logs. They're just so commonly seen in calculus that you have to spend that much extra time with them just to familiarize yourself through the derivative procedures and later on through the integral procedures. Natural logs are one of my favorite functions to address. Therefore I take little to no shame when it comes to presenting more and more videos for natural logs. I just don't mind presenting natural logs in any way. Our first question is not going to be hard. It's going to be this. We have to find the derivative of this, and you know when we were talking about derivatives, the common aspect of derivatives or the end point is that you are determining some kind of slope of a tangent line, the instantaneous rate of change. That's what we're doing when it comes to differential calculus, because that slope of the tangent line gives you your equation of the tangent line from which you can have the application arrive. But in this video we'll be looking at the derivative techniques for natural logs. You know this right as a composite, so you treat it as such. You do u is equal to x squared plus 10, and then f of u is equal to ln u. So this right here is going to be an easy question. Derivative with respect to u, ln u, and then the derivative with respect to the actual composite substitution part is going to be in this parenthesized part right here. Ln u derivative is 1 over u. You know the basic scheme for natural log ax is 1 over x. You know that's the derivative scheme. For the most basic natural log function, it always becomes 1 over x. Ln u becomes 1 over u. X squared plus 10 becomes 2x. You end up with 2x over u, which translates into your final answer 2x over x squared plus 10. Then you are done. So all of these questions here represent some sort of a function. It would have been f of x is equal to whatever I'm calculating the derivative of. Here this entire aspect is our composite, so you have to treat it as such. If u is equal to ln x, then f of u is equal to u to the power of 1 over 5. See, u to the power of 1 over 5. Fifth root radical, 1 over 5. You proceed in that way. Basically for these chain rules, you just have to know how to substitute or what to substitute correctly so it takes you down the right path. U to the 1 over 5 and then du over dx is just ln x, which will be easy. The hardest part is right here, but this is not hard in terms of the power rule. 1 over 5 u to the power of minus 4 over 5. 1 over 5 comes here as a coefficient. The exponent is reduced by 1, minus 4 over 5. Ln x becomes 1 over x. To do the final part over here, I'm bringing these x and the 5's together. Everything will be with the denominator 5x. U to the 4 over 5 will come down with a positive exponent. See, u to the 4 over 5. Our final answer will be right over here, 1 over 5x. And you'll resubstitute for u, which was ln x. See, ln x. But ln x is to the power of 4. And all of this is to the fifth root. Fifth root. And that right there will represent your final answer. It's 1 over all of this. This entire part is a denominator. This question is a slight variation from the one before. In the previous one, the fifth root was affecting everything. Here, the fifth root is affecting only the variable. Chain rule again, u is equal to x to the 1 over 5. You see how I wrote this like that? In the exponential form, f of u is equal to ln u. So now it's not going to be hard. Ln u and then du over dx. The chain rule is so commonly employed in these techniques that it becomes second nature. This derivative becomes 1 over u, this derivative becomes 1 over 5, x to the minus 4 over 5 using the power rule. You can bring everything in the denominator where it will end up using the 5 first, then followed by the u, then x to the minus 4 over 5, but you have to substitute for u. And I'm making a little error over here because I'm seeing a minus 4 over 5, but when I brought it down it should become positive 4 over 5, but it's fine, I caught it. It's x to the 4 over 5. Substitute back for the u. 1 over 5, x to the 1 over 5, x to the 4 over 5. See, both of these have to be brought together. This was my u, x to the 1 over 5, and this x to the 4 over 5 generated from this numerator coming down. These things can be brought together using the law of exponents such that you end up with 1 over 5x as your final answer and you're done. And you can see this yourself. x to the 1 or 5 times x to the 4 or 5, the exponents add. You get 5 over 5, which is just a 1, and the question is completed. So there are a certain number of questions that I want to go through in this video, and I apologize if any of these questions end up being repeat from a previous video. I tried my best to avoid that aspect that I repeat a question which I presented in another video, and I hope I succeeded in that task. When we're looking at this rational function, we're thinking about the quotient rule. We have the f function and the g function, and we have to proceed with that. We'll just lay it out over here, then we'll start solving it over here. The g function and the f function in the quotient rule template. 1 minus ln x, which is the g function, which will multiply by the derivative of the f function, 1 plus ln x. And due to space limitation, let's come over here with our minus sign. We'll put the f function 1 plus ln x, which will multiply by the derivative of the g function, which will be calculated. And all of this numerator will be dividing by the g square, which is 1 minus ln x. It'll square with all of that. So we have to do this top and numerator aspect out, and we'll somehow combine it with the denominator, and let's see how everything will play out. We'll come over here. This 1 minus ln x will remain unaffected. Derivative of 1 plus ln x is a derivative of a polynomial. The derivative of 1 is 0, but the derivative of ln x is just 1 over x, so that was easy. Then we write over here 1 plus ln x. The derivative of 1 minus ln x is easy. This is 0. This will be minus 1 over x. And this will be all over this 1 minus ln x squared. Now all we have to do is simplify the numerator. Let's rewrite everything with these over x's, the denominators. 1 minus ln x over x minus 1 plus ln x over x. But let's not forget this minus over here impacts with this minus over here and makes it a positive. See, minus 1 over x multiplies with that minus and makes it positive. This right here is all over the denominator, 1 minus ln x squared. This is basically just the algebra part. The hardest part was this part right here being the derivative. Now we can do simplification. Everything here in the numerator is in over x. 1 minus ln x plus 1 plus ln x's. The ln x's will cancel out because you have a negative ln x, positive ln x. You essentially have 1 plus 1 is a 2 over x. But this 2 over x and this over denominator will come with it, 1 minus ln x squared, and this right here will be your final answer right over here. And you can see it. It's just algebra right here. That's all what it is. But this right here is your final completed answer. Here is a question that will prove to be very exciting, because think about it. You have a composite function right over here. Within the composite function you have a product rule, but within the product rule one of the items is a composite in itself. Here with an initial substitution, which will be u is equal to x to the 4 sine square x, and then f of u is equal to ln u. We'll have ln u, and then we have du over dx, x to the 4 sine square x. Here we have to do the product rule, and natural log u derivative, we can bring it out as a 1 over u, because I've done the derivative of ln u, I've made it 1 over u, and here I'm going to lay out the template for the product rule. You'll have the f function and the g function. The g function will multiply by the derivative of the f function, and then you'll add the f function to the derivative of the g function, but the g function is a composite. Sine square x is a composite. So let's bring in another substitution. V is equal to sine x, f of v is equal to v square. V square, and then dv with respect to x is sine x. That's the entire product rule with the new chain rule laid in, because the sine square x was a composite. And we did the v was equal to sine x. Then f of v was equal to v square. So you'll see that right over here, v square, and then dv with dx is sine x. A little complicated, but not unnecessarily hard. 1 over u, and let's do this entire parentheses part. The derivative of x to the 4th is 4x cubed, which I'll write over here with the sine square x, plus the derivative of v squared is a 2v. I'm only borrowing the 2 out of that, and I'm writing x to the 4th. I still have the v, and I still have the sine x, which comes out as a cosine x. Alright, this is what we have so far. Now let's rewrite everything here with the u underneath, because this over u is the denominator of all of this. So let's come over here, 4x cubed sine square x plus 2x to the fourth. Let's bring the cosine x first and put the v. What was v? V was right here, sine x. See, v was equal to sine x. All over u, x to the fourth sine square x. Now you have to do simple simplification basically. You're seeing commonalities here and commonalities here. Things might be able to cancel out. Isolate. From the numerator, there's a 2, there's an x cube, there's a sine x in all the terms. 2x cubed sine x goes right in here 2 times. See, 2x cubed sine x goes in there, actually 2 sine x times, because there's a sine x over here and I isolate only a sine x. 2x cubed sine x goes in all of this, x cosine times x cosine x, x cosine x, all over x to the 4 sine square x. Now you can cancel things out here, so I will write the final answer. This is why I was saying it's going to be slightly more involved, but it wasn't harder, it was just more involved. X cubed will cancel out with this x to the fourth, so that you'll have only an x remaining on the bottom. Sine x will cancel out with the sine square, so you'll only have sine x remaining on the bottom. On the bottom you'll have x sine x. The x cube and sine x got cancelled out and consumed. Here you'll have 2 sine x plus x cosine x, and this right here will be your final answer. It wasn't a hard question, but there was a lot of opportunity in this question to make a silly mistake, and that silly mistake could carry its way out and then corrupt the entire response. So let's look at this question right over here. Natural log tan x compounded by this composite, which is an exponent, a composite exponential form of a derivative function we have to do. We will do a substitution. U is equal to natural log tan x. Then function with regards to that u is u square. See, u square. That's all we need to know to finish this question. D over du, u square, and then du over dx, ln tan x. And I might have been premature when I said that's all we need to know, because we have another composite playing here. So v is equal to tan x. Then function with regards to v is ln v. So we have a chain developing right over here. D over du, u square, du over dv, ln v, and then dv over dx, tan x. Do the things, derivatives. U square comes out as a 2u, ln v becomes 1 over v, tan x becomes a secant square x. Bring all the numerator items together and all the denominator items together, which is not much. You have 2 secant square x. Resubstitute for u, which is natural log tan x over v, which is tan x, and this represents a complete final answer right over here. Here is a slight variation of the previous question. Previously, this entire function was compounded by that exponent, but here you're basically affecting only the tangent with this exponent. You could look at it as this. You have this parenthesized and natural log outside. How can you proceed with this? In one way, you can do u is equal to tan square x, then f of u is equal to ln u, and you can proceed with that. D over du ln u, and then du over dx tan square x. But here you have a composite, so v is equal to tan x, then f of v is equal to v square. And then you can come back over here, d over du ln u, and then du over dv would be v square, and then dv, that should be in a u over here, dv over dx is equal to tan x. Now you just have to do the derivative over here, 1 over u, 2v secant square x. Substitute. 1 over u became 1 over tan square x, right? Tan square x. V was a 2v. Let's bring the 2 out here with this 1 and just change the 1 into a 2. V was what? A tan x. Tan x. And then we had a secant square x right after that. Secant square x. You can simplify it. You see there's one tan x here and tan square x. This tan x can cancel out that square. You end up with 2 secant square x over tan x, and that's your final answer. Now, if you remember very quickly in this video, I said that one way we can do it was this. This was one way. The other way may have been the smarter way, where you use the properties of logarithms and you simplify your entire question. Think about this. Anytime you see something which looks like ln x squared, and I'm using just x squared, you can bring this right over here, right? 2 ln x. You remember that property, right? Where the exponent becomes a coefficient of the entire natural log. Well, you can do exactly what you're seeing over here with regards to this question. You basically have ln x squared. X just happened to be a tan. You could have viewed this entire question as 2 multiplied by the derivative of natural log tan x, because the exponent of tan came out here. Now you can do a simple chain rule substitution and end up with the same answer, ln u and then du over dx tan x. Derivative of ln u would be 1 over u. Derivative of tan x is a secant square x. When you resubstitute back u, which was tan x, you get 2 secant square x over tan x, and you end up with exactly the same thing right over here and right over here. The harder way, and perhaps the less sophisticated way, the easier way, and perhaps a more sophisticated way, because here you use a property of logarithm to simplify your entire process. And this right here represents a higher level of sophistication versus doing it this way. Again, these are all perfectly legitimate questions from my single variable textbook, nothing hypothetical. We have this function over here, a composite within a composite. This right here should be our first substitution right over here. U is equal to cosine ln x, and then f of u is equal to ln u. And we'll start with that. Derivative with regards to u, ln u, and then du over dx cosine ln x. But we won't go right there because we have to do another substitution. If v, the other substitution is right within here. If v is equal to ln x, then f of v is equal to cosine of v. And you'll see that play out right over here. Du over dv cosine v, and then dv over dx ln x. This double chain or double substitution captures entirely everything you see here at the top. You have to do the derivative. Now each of these, ln u becomes 1 over u, cosine v becomes sine v, but you know cosine generates a minus. I'm just putting the minus right out over here because the derivative of cosine is a minus sign. Ln x derivative is 1 over x. Now we have this minus come here, we have the sine. Sine v must attach back to its original substituent. V was ln x right over here, ln x all over u and x. I'm putting the x first, but what was u? U was cosine ln x right here. See, u was cosine ln. This right here is your final completed answer. So we end our video on a high note with this question, and by high note I mean we ended with an easy question. Why not? 2 minus x minus 5x squared, f of u, or function with regards to u, is ln u. Chain rule, single chain kink over here, ln u, and then du over dx. We have a polynomial over here, and you know polynomials are one of the easiest when it comes to derivations. Derivatives of polynomials are the easiest. The natural log is 1 over u. Actually, you might say the derivative of a natural log might be easier because you're just doing 1 over. That's much easier than doing this. The derivative of a constant is a 0. Derivative of this minus x will just come out as a 1, you know, because it's x to the power of 1. You use the power rule, 1 comes over here and the exponent is reduced to a 0. You'll get minus 1 x to the power of 0, which is just a minus 1. And here you'll get a 10x. When you simplify everything here, and the simplification involves removal of 0 only, minus 1 minus 10x over u, which was 2 minus x minus 5x squared. You can say this right here is your good final answer, but there's a better, more sophisticated final answer, because it's by convention you don't want to be bringing minuses here in the numerator. If you can avoid it, you should avoid it. You'll multiply everything over here by a minus 1. And you'll change the signs around. You'll get 10x plus 1 over, and you'll write things in from high order of degree of variable to low order or degree of variable. This will become 5x squared plus x minus 2. You see how the minus has changed? Minus 1 has flipped all the signs around, but this right here is the best final answer right here. And with this question we end our video. I hope you enjoyed this, let's call it a part 2 natural log derivative video, because I already presented a part 1. And I don't think we'll be looking at much more derivatives of natural logs after this. If at all, it'll be incidental or indirect as they appear maybe in integrals when we're looking at the fundamental theorem of calculus and how things go backwards, flip-flop. We may come back at a topic like this later on then. Anyhow, for now, I think we've delved into natural logs quite a bit. If there's another video coming after this with regards to natural logs, it'll probably be for a specific purpose or something I found it necessary to present. But I hope you enjoyed this video and the comprehensive nature of the natural logs or the logarithm derivatives we looked at. Please stay tuned because I have multiple new videos on the way, and we still have to delve into the concepts and the topics of integral calculus, which is a whole new ball game right over there. But stay tuned, and I appreciate you all watching my videos. Have a nice day. Bye.